Okay, so now we will do the same thing that is really cool, which is like the Schumacher theorem. Like, what he invented, this man Schumacher, and just that he given a definition of the typical subspace we need, like how to say it, like you have like you just have in a way that's um, oh let me talk. So basically, like he said, like if alpha is strictly superior to HA of P, then there exists an N alpha S compression scheme for source for A for all between T mini N bleeding into N. So just say like you can compress if alpha is superior to HA of P. It's just like if the rate of compression, um, you compress, so you have first your space, and after you compress with alpha. In the way this alpha, this is the stuff at the beginning. Here, like it's just the entropy. Like the entropy should be included less or more into alpha. Yeah, like because you need to have all those entanglement, all this uncertainty that you can find into alpha. That's what it means. Like so, the exact definition is just this. Like there is an alpha S compression scheme for source row A. So yeah, here it will be called row A if you prefer. For all infinitely mini n infinity. Because like and that's all the power of Schumacher. He just takes this entropy and gave an operational meaning of it, where he says finally like at the end the size of this typical subspace that is correlated to it. It just correlated to the entropy stick. 2 to the power of 2 to the power of 1 n by ha of rho. So typically, if you take a concrete example about it, suppose like you have like I don't know, like nine, yeah, you know what? Let's go. 81% of chance of having 0, 19% of chance just having 1, and you just take 1000 qubits, and either 0 either 1. The entropy, it just minus rho log rho, so it's just like this. And so this 0.7 is just for alpha limit, it just say at the end that you can compress at let's or more 70%, because like the fact is just like you just need like most of the time by probability you'll have 810 times 0 on 100 1901 190, because like that's a percentage, like, and so your typical subspace is just having 810 on 191. You don't know the order, but by doing this you just reduce a lot your typical subspace where you compress, and so you just say thanks to the entropy that you have, like we can compress into 70%. So if you take our scheme now, so have your source for A, etc. And so if you calculate the typical substate, the size of it. Um, we just know that it will just be equal to 2 to 1000 multiplied by HA of P, which is like equal to 2 to 1000 multiplied by 2 to the power of 700. So it just like to conserve the uncertainty inside all the stuff. Here it will be 2 to the power 700, and here 2 to the power of 1000 at the exterior of it. And so that's why that's cool, you just reduce it, and Schumacher just find a way to express that if you conserve the entropy, then if your rate of compression is super to entropy, then it's cool, like you can do what you want. But if it is not, and the more the n will be big, the better will it be. But if you have your entropy like is bigger than your rate of compression, so you have like as earlier if HMIT is it like euro A, and so you have your entropy and your rate of compression is like that, and here is like your entropy, um, like how to say here alpha AG of P. Then it's not cool because like you cannot with alpha you miss all of this, and there could be quantum correlations there, and so it does not work. Like there exists an alpha S compression scheme uh, for source at rho a for at most finitely many n. So just mean like you may be at the beginning when you have few n, like few qubits, 1 or 2 or 3, having some luck, and so it will work. But when you take like 1000 qubits, like, it will not work because there is all those problem of quantum correlation that could be not be included into, and so all the genius of Schumacher just to find an operational interpretation of the quantum entropy to finally like determine the size of the typical subspace being 2 to the power of n by this entropy.